Hey physicists, we're going to take a look at practice 1 motion maps, problem number 1 and 2. So take a look at this after you've completed, given it a shot, see how your answer compares to these. Okay, and you've already seen that for each situation. To the right is the positive direction. Okay, so you're going to sketch a motion map and a position versus time graph that corresponds to the following descriptions of the motion of an object. In our previous examples, we actually saw the motion, and this time we just have a word model of what's happening. Okay. We're going to add numbers to the graph and the motion maps, and we want our first dot to be a time of 0 seconds. Okay, so let's take a look at this. Number 1, an object moves at a speed of 4 meters per second to the right for 3 seconds, starting at a position of 0 meters. Okay, so let's take a look at how far we're going to move. I'm going 4 meters per second for 3 seconds. My displacement, delta x, remember that from the reading, is going to be 12 meters. So I want to make sure that my motion map can cover 12 meters. I'm starting at 0, 2, 4, 6, 8, 10, 12 meters. I put the numbers below, it just makes it a little easier to see the motion map in just a few moments. Okay. Hey, so now I'm going to cite where the object is at each second. Hey, so we know our object is starting at 0 meters. 1 second later, it's traveled 4 meters per second, so it's traveled 4 meters. That puts our object at 1 second at 4 meters, at 2 seconds at 8 meters, at 3 seconds at 12 meters. We're going to go ahead and label these with the time. So that first one, our time is equal to 0 seconds, and we're at 1 second, 2 seconds, 3 seconds. Let's go ahead and put some arrows to indicate the direction that we're traveling. And we're going from one dot to the next. The arrow points in the direction that the object is traveling. Longer arrows indicate faster motion. All right, so we have our motion map complete. Let's go ahead and transfer this information over to the position versus time. Hey, so along the horizontal or independent axis, I'm going to put my time. I can see I go from 0, 1, 2, and 3 seconds. Based on the number of ticks here, I can go 0, 1, 2, and 3 seconds. If I look along the vertical axis, I'm looking at the position. I've got to cover 12 meters of movement here. I have 1, 2, 3, 4, 5, 6, 7 ticks. It looks like if I go with 2 meters for each of those ticks, I can cover the motion really very nicely. Okay, hey, so we have our graph all set up. Okay, let's go ahead and transfer our points. So at a time of 0, I'm at a 0 position. At a time of 1, I'm at 4 meters. At a time of 2, I'm at 8 meters, 2 seconds and 8 meters. And at a time of 3, I'm at 12 meters, or at least our object is. Okay. Let's go ahead and we'll put a nice best fit line in there. Just hand drawn here. There. If we were to take a look at the slope of this line, we'll pick two spots that pass through grid marks. We'd find out the slope of this line is 4 meters per second. Check, see how your drawing looks compared to this. We didn't have to figure out the 4 meters per second, but we know it's done right if the slope of this line on the graph shows 4 meters per second, because that was assigned to us in the problem. Hey, make sure that you've tried number 2 before checking the solution here. Hey, in situation 2, we have an object is standing still for 5 seconds at a position of 10 meters. So we know that our motion map and also our position graph, our position versus time graph, is going to have to cover at least 10 meters. Hey, so it looks like we could end up using pretty much the same scale as before. I'm going to change the color there. So again, I can go 2, 4, 6, 8, 10 meters along here. Hey, now we end up having an object standing still for 5 seconds. In our example problems. We ended up having a bug that went along. It was dropping some ink every second. Another way we could say it's pooping as it goes along, pooping once every second. So we have an object, we can think of it as the bug is standing still for 5 seconds at a position of 10 meters. What would happen if it ended up pooping at a time of 0? Yep, okay, let's go ahead and put that there. Okay, it pooped again, and it pooped again. 2, 3, 4, 5. Okay, it just keeps building up at the same spot there. Okay, and so this is for a time of 0 all the way to 5 seconds. Because it's not moving, there's no arrows involved in there. Let's go ahead and transfer the data over to our position versus time graph, another way of representing that motion. Hey, we see we have to cover up to 5 seconds. Hey, so we can't quite have it the time spread out as much as we did here. Let's go ahead with 1, 2, 3, 4, and 5 seconds. Hey, our vertical position is going to be pretty similar to what we had before. 0, 2, 4, 6, 8, 10, 12, and 14 meters. Go ahead and transfer the data. At a time of 0 seconds, it's at 10 meters. 0, 10 meters. At a time of 1 second, it's at, guess what? 10 meters. At a time of 2 seconds, it's at 10 meters. At a time of 3 seconds, it's at 10 meters, 4 seconds, and 5 seconds. Hey, so our position is not changing with time. How do we end up seeing or looking at a graph where the value on the vertical axis is not changing? We end up getting a horizontal line. Yep, so this is saying our position is not changing as time goes along. Our motion map shows that the object stayed in one position. Our position versus time graph shows the same thing. See how this compares to what you had for number 2.